When we use the word system, we mean an object or collection of connected objects that are of interest to us. Systems have inputs and outputs, and in this video we are going to establish the basic properties of systems that are useful to us. We will limit ourselves to a particular class of systems in this course, linear systems, and we will introduce a key idea that is central to the study of linear systems, namely superposition. The learning objective introduced is to appreciate how linearity, superposition and convolution provide a framework for determining the response of a linear system to arbitrary inputs. This video will introduce two key ideas, linearity and superposition. Let's start with a simple system, fluid flowing into a container. The input here is the flow rate of fluid, which we measure with units of meters cubed per second. As the output, we can choose the height of fluid in the container. The faster fluid flows, the faster the height rises. How do we model this? If the container has straight sides, its cross-sectional area will be constant, say A metres squared. If the flow rate of water into the bucket is Q metres cubed per second, then the rate of change of height of water, measured in metres per second, is given by a first-order differential equation. The derivative of water height h with respect to time is equal to the flow rate Q divided by the cross-section area A. Note that this equation is dimensionally consistent. Our model allows us to predict the rate of change of water height for different flow rates. Most dynamic systems have inputs that affect the time rate of change of the outputs. However, we are usually more interested in the outputs and not their derivatives. For this reason, we write the system dynamics as an integral equation rather than a differential equation. Here is a block diagram representation of the system. The inverse of the container's area acts as a scaling after the integrator. Note the flow rate of water, the input, the volume of water in the bucket, an internal variable, and the height of water, the output. The initial condition for the differential equation is the output of the integrator at t equals 0, that is the initial volume of water in the bucket. We can reverse the order of the blocks, so the internal variable becomes the rate of change of height. The initial condition for the integrator is now the initial height of water in the bucket. We are able to reverse the order of the blocks because the system is linear. We will elaborate on the meaning of linearity shortly. It is easy to calculate the height of water in the bucket given the time history of flow into the bucket. It's just the area under the graph Q with time divided by A at any time plus the initial height of water. Suppose there is a hole in the bucket. Water will now leak away at a rate determined by the height of water. For simplicity, let's assume the outflow is proportional to the height. Let's also assume the container is initially empty. The net flow of water flowing into the bucket can be integrated to get the volume. To obtain the height, divide the volume by the cross-sectional area. The flow rate from the bucket is the height of water multiplied by a constant K, which we'll call the orifice constant. It has units of meters squared per second. The net flow of water to the container is the difference between the flow in and the flow out. This can be represented with a summing junction, which is shown as a circle. Note a feedback loop has materialised in describing the system. Feedback often materialises out of the physics of systems. The mathematical equation governing this system can be determined directly from the block diagram. The time derivative of the height is the difference between the flow in and the flow out. If we put all terms involving the unknown or dependent variable h on the left, the governing equation becomes. We call this a forced first-order, linear, time-invariant ordinary differential equation. That's quite a mouthful. Let's break it down. It's first order because the highest derivative of the dependent variable h is the first derivative. A second-order equation would have the second derivative as the highest derivative. A third order, the third derivative, and so on. The system is linear because the dependent variable h and its derivatives appear as linear combinations. That is to say, they sum together or subtract from one another after possibly being scaled. Now, if one or more of the dependent terms was squared, square rooted, or we took its cosine or absolute value or applied pretty much any other mathematical operation to it, other than multiplying it by a scaling factor, the equation would be nonlinear. It's time invariant because the coefficients of terms involving h are constants. They're independent of time. It's forced because it's driven by an input, here the inflow denoted by q. The response of h to a given input q is called the forced response. If we set the inflow to 0, the equation becomes unforced. An unforced system will still have a response that varies with time if it has non-zero initial conditions. For example, a container with a hole in it will empty if it contains water. The response of a system due to its initial conditions is called the free response. The systems we're interested in are linear systems. Now, real systems are rarely truly linear, but they are often closely approximated by them. Linear systems serve as a very useful approximation because they have well-defined mathematical properties. The most important property applicable to all linear systems is the principle of superposition. This important principle allows the response produced by the simultaneous application of two or more inputs to a linear system to be computed as the sum of the individual responses to those inputs. This prop demonstrates the idea. I can half fill the container with one fluid and top it up with a second, or we can pour them together. Either way, the overall height is the sum of the two. The fluid height superimpose. Not bad. Let's look at this example in more detail. To understand superposition, suppose there's no water in the container. That is, the initial condition on h is 0. Suppose also that the total flow rate can be thought of as having two parts. Call them Q1 and Q2. The height of water will be the sum of the individual solutions of the governing equations, where Q1 and Q2 act alone. A mathematical description is shown on the right. The two concepts introduced in this video are linearity and superposition. The analytical techniques we will use are all founded in the mathematics of linearity. And the causal system models we are interested in are linear systems. Linear systems can be described by linear ordinary differential equations. Superposition is a key property of linear systems, and it keeps appearing throughout the course in different guises. Superposition allows the overall response of a system to be found by summing the response of the system to component inputs and the response due to initial conditions. For example, by finding the overall response by summing the forced and free responses.